हम इस मेटल स्फीयर के पास में कोई रॉड लेके आते हैं, मान लेते हैं इसके ऊपर पॉजिटिव चार्ज है, तो जैसे ही इस रॉड को इससे टच करेंगे इस पे पॉजिटिव चार्ज आ जाएगा। अगर पॉजिटिव चार्ज आएगा तो ये चार्ज स्प्रेड होता हुआ इन फॉइल्स पे भी आएगा और ये दोनों फॉइल्स एक दूसरे से डाइवर्ज हो जाएंगे। जितना ज़्यादा चार्ज होगा उतना हम ये कह सकते हैं फॉइल ज़्यादा डाइवर्ज होगी। तो दो अलग अलग केसेस में अगर एक रॉड है और एक दूसरी रॉड है, दोनों पे चार्जेस हैं, जब उनको ला के यहाँ पे टच करेंगे तो जिस केस में ज़्यादा फॉइल्स डाइवर्ज हो रही हैं हम ये कह सकते हैं वहाँ पे ज़्यादा चार्ज है। तो चार्जेस को कंपेयर करने का कम या ज़्यादा मैग्नीट्यूड को क्वालिटेटिव मेजर करने का सबसे अच्छा तरीका है। हाउएवर इन द सिचुएशन हम मैग्नीट्यूड भी मेजर कर सकते हैं, लेकिन फंडामेंटल लेवल पे हमारे सिलेबस में ये नहीं है। इनके बीच के फॉइल्स के बीच का अगर एंगल थीटा है तो हम ये कैलकुलेशन कर सकते हैं कि किस चार्ज की वजह से कितना एंगल डाइवर्ज होगा बाय कंसीडरिंग द इक्विलिब्रियम ऑफ दीज स्ट्रिप्स। सो वहां से मैग्नीट्यूड भी मेजर किया जा सकता है, लेकिन अभी हम सिर्फ इसका क्वांटिटेटिव की बजाय क्वालिटेटिव मेजरमेंट कंसीडर करेंगे। सो दो तरह की पॉसिबिलिटी है जिस केस के अंदर फॉइल्स के डाइवर्जेंस की एनालिसिस किया जाता है। पहला तो इस मेटल रॉड को टच करें, दूसरा टच ना करके अगर दूर से भी पास लाएंगे। सो क्योंकि ये मेटल स्फीयर है हम ये कह सकते हैं इन केस ऑफ मेटल स्फीयर अपोजिट चार्ज इंड्यूस होगा। टच करेंगे तो सेम चार्ज इंड्यूस होगा और अगर टच नहीं करेंगे तो इन दिस सिचुएशन अगर मान लीजिए यहाँ पे नेगेटिव रॉड लाते हैं तो यहाँ पे पॉजिटिव चार्जेस इंड्यूस होंगे इसके ऊपर, और जो यहाँ पे पॉजिटिव चार्जेस इंड्यूस होंगे उसकी वजह से यहाँ पे अपोजिट साइड यानी फॉइल्स के ऊपर नेगेटिव चार्जेस इंड्यूस होंगे और वो नेगेटिव चार्जेस इस फॉइल को डाइवर्ज कर देंगे। अब अगर इस रॉड को दूर हटा दिया जाता है तो आप ये कह सकते हैं कि चार्ज न्यूट्रलाइज हो जाएगा और फॉइल्स वापस अपनी न्यूट्रल स्टेज में आ जाएंगे। सो डिफरेंस बिटवीन द टू स्टेट्स जो मैंने बात करी थी, अगर टच कर रहे हैं तो कंडक्शन से एक्चुअल चार्ज ट्रांसफर हो जाएगा, फिर उसको न्यूट्रलाइज करने के लिए कोई नेगेटिव चार्ज देना पड़ेगा। लेकिन अगर इंडक्शन से कर रहे हैं, आप सिर्फ पास में ला रहे हैं, तो अपोजिट चार्जेस इंड्यूस होंगे और चार्जेस का रफ मेजरमेंट उसके बावजूद भी होगा, क्योंकि अगर रॉड पे चार्ज ज्यादा है तो वो ज्यादा चार्ज इंड्यूस करेगा, फॉइल्स ज्यादा डाइवर्ज होगी। सो गोल्ड लीफ इलेक्ट्रोस्कोप का बेसिक पर्पस होता है चार्ज का फंडामेंटल लेवल के ऊपर मैग्नीट्यूड मेजर करना, या ये कहें दो अलग अलग चार्जेस है तो उनके मैग्नीट्यूड का कंपैरिजन करना, जिस पर्पस से गोल्ड लीफ इलेक्ट्रोस्कोप काम में आता है। आइए आगे बढ़ते हैं नेक्स्ट पॉइंट पे, चार्ज की बेसिक कैरेक्टरिस्टिक के ऊपर, जिसपे भी बेसिक लेवल पे कई बार क्वेश्चंस पूछे जाते हैं। बेसिक कैरेक्टरिस्टिक के ऊपर जिस इलेक्ट्रोस्कोप काम में आता है। आइए आगे बढ़ते हैं नेक्स्ट पॉइंट पे, चार्ज की बेसिक कैरेक्टरिस्टिक के ऊपर, जिसपे भी बेसिक लेवल पे कई बार क्वेश्चंस पूछे जाते हैं। थैंक यू भोजी। सो स्टूडेंट, अब हम बात करेंगे प्रॉपर्टीज ऑफ इलेक्ट्रिक चार्ज और चार्जिंग की। किसी भी सिस्टम में जब हम चार्जेस की बात करते हैं, इलेक्ट्रोस्टैटिक्स में स्टैटिक चार्जेस के बारे में हम डील कर रहे हैं। सो सबसे ज़्यादा ज़रूरी यही समझना है कि चार्जेस बिहेव कैसे करते हैं। तो प्रॉपर्टीज़ में सबसे पहली प्रॉपर्टी हम कह सकते हैं चार्ज का क्वांटाइजेशन। क्वांटाइजेशन का मीनिंग होता है कोई भी ऐसी फिजिकल क्वांटिटी जो स्टेप्स में चेंज होती है उसे हम क्वांटाइज क्वांटिटी कहते हैं, और जो फिनोमेना है जिस तरीके से उस क्वांटिटी को चेंज किया जाता है उसे क्वांटाइजेशन कहा जाता है। सो जब हम चार्ज क्वांटाइजेशन की बात करते हैं इसका मतलब ये है कि चार्ज ऑन एनी बॉडी कैन बी रिप्रेजेंटेड एज एन इंटीग्रल मल्टीपल ऑफ इलेक्ट्रॉनिक चार्ज। ई हम इलेक्ट्रॉनिक चार्ज 1.6 × 10⁻⁻19 कूलम लेते हैं। एग्जैक्ट वैल्यू आप एनसीईआरटी में देख सकते हैं, दी हुई है। सो Q इक्वल टू एनी में n यहाँ पे है सेट ऑफ इंटीजर्स, यानी किसी भी बॉडी पे अगर कोई चार्ज दिया जाएगा तो वो E का मल्टीपल होगा। क्यों? क्योंकि चार्जिंग की ही जाती है इलेक्ट्रॉन के एडिशन या रिमूवल से। अगर हम यहाँ पे चार्जिंग की बात करें तो चार्जिंग का डायरेक्ट मीनिंग होता है एडिशन और रिमूवल ऑफ इलेक्ट्रॉन। इस चीज का आप ध्यान रखेंगे। इलेक्ट्रॉन हटाएंगे बॉडी पॉजिटिव चार्ज हो जाती है, इलेक्ट्रॉन डालेंगे बॉडी नेगेटिव चार्ज हो जाती है। सो बेसिकली चार्ज इज अ क्वांटाइज क्वांटिटी। अनदर पैरामीटर चार्ज इज कंजर्व्ड क्वांटिटी। टोटल सिस्टम का चार्ज हमेशा कंजर्व्ड होता है। एडिटिव सब्ट्रैक्टिव होता है चार्ज। जितने भी चार्ज पॉजिटिव नेगेटिव दोगे वो सिंपली ऐड हो जाएंगे या सब्ट्रैक्ट हो जाएंगे। तो बेसिक चीजें हैं, मैं चेकलिस्ट में ज्यादा डेप्थ में नहीं जाना चाहूंगा। लेकिन इंपॉर्टेंट चीज एक और है, जब हम कंडक्टिंग या नॉन कंडक्टिंग बॉडीज की बात करते हैं, ये चीज आपको बहुत ध्यान से दिमाग में रखनी है कि कंडक्टिंग बॉडीज की अगर हम बात कर रहे हैं तो आपको हमेशा ध्यान में रखना है कंडक्टिंग बॉडीज या मेटल बॉडीज के केस में अगर बॉडी को कोई भी चार्ज सप्लाई किया जाता है तो वो चार्ज हमेशा इसकी आउटर सरफेस पे रिटेन्ड रहता है और इसके अंदर इलेक्ट्रिक फील्ड का वैल्यू हमेशा 0 रहता है। या ये कहें कि चार्ज ऐसे डिस्ट्रीब्यूट हो जाता है कि इसके अंदर हमेशा इलेक्ट्रिक फील्ड 0 होता है। इलेक्ट्रिक फील्ड आगे हम पढ़ेंगे, बट क्योंकि हम चेकलिस्ट की बात कर रहे हैं सो बेसिक पॉइंट आपको ध्यान में रखना है। नॉन कंडक्टिंग बॉडीज की बात हम करें, अगर इंसुलेटर्स की बात करें सो इंसुलेटर्स के केस में अगर बॉडी को कोई चार्ज दिया जाता है तो जिस तरीके से चार्ज देंगे वो उसकी बॉडी में डिस्ट्रीब्यूटेड रहेगा, यूनिफॉर्मली और नॉन यूनिफॉर्मली, इट डिपेंड्स कि आपने चार्ज दिया कैसे है। तो यूनिफॉर्मली या नॉन यूनिफॉर्मली डिपेंड्स। क्वेश्चन में हमेशा आपको गिवन होगा कि चार्ज यूनिफॉर्मली डिस्ट्रीब्यूटेड है या नॉन यूनिफॉर्मली डिस्ट्रीब्यूटेड है। सो इस चीज़ को हमेशा ध्यान में रखना है। बॉडी के अंदर अगर चार्ज है तो ऑब्वियसली यहाँ पे ना तो अंदर इलेक्ट्रिक फील्ड जीरो होगा ना ही बाहर इलेक्ट्रिक फील्ड जीरो होगा। मेटल में बाहर इलेक्ट्रिक फील्ड हमेशा नॉन जीरो होगा क्योंकि चार्ज की वजह से इलेक्ट्रिक फील्ड पॉजिटिव है तो अवे होगा, नेगेटिव है टुवर्ड होगा। बेसिक पॉइंट हमेशा ध्यान में रखें कि पॉजिटिव चार्ज की वजह से इलेक्ट्रिक फील्ड अवे होता है और नेगेटिव चार्ज की वजह से इलेक्ट्रिक फील्ड इनटू द चार्ज होता है हर पॉइंट पे। और इसी तरीके से हम फील्ड लाइंस को भी आगे रिप्रेजेंट करेंगे, जब फील्ड लाइंस के बारे में बात करेंगे तो थोड़ा डिटेल में डिस्कस करेंगे। सो बेसिक चार्ज की प्रॉपर्टीज को आपको हमेशा ध्यान में रखना है। इलेक्ट्रिक फील्ड जो जीरो रहता है मेटल में रहता है और इस इलेक्ट्रिक फील्ड जीरो को कोई एक्सटर्नल चार्ज भी नहीं बदल सकते। यानी अगर अपन यहाँ पे इंडक्शन की बात करें, विच इज ऑल्सो वेरी इंपॉर्टेंट कॉन्सेप्ट, इंडक्शन ऑफ चार्ज। सो आप ये कह सकते हैं कि अगर किसी न्यूट्रल मेटल बॉडी जिस पे चार्ज जीरो है, अगर इसके बाहर कोई प्लस क्यू चार्ज रखा जाता है तो प्लस क्यू इसके इलेक्ट्रॉन्स को अट्रैक्ट करता है, इसके सामने नेगेटिव और पीछे पॉजिटिव चार्ज आ जाता है। यानी यहाँ पे बॉडी में चार्जेस सेपरेट हुए हैं। अगर इस बॉडी को बीच में से काट दिया जाए तो लेफ्ट पार्ट नेगेटिव हो जाएगा, राइट पार्ट पॉजिटिवली चार्ज हो जाएगा। सो इट ऑल डिपेंड्स ऑन द टाइप ऑफ चार्जेस जो इसके बाहर रखे गए। अगर यहाँ नेगेटिव रखेंगे तो अपोजिट पोलैरिटी आ जाएगी। इस तरह से अगर ऑलरेडी चार्ज बॉडी है हमारे पास, अगर ये पहले से चार्ज होती है और यहाँ पे कोई चार्ज लाया जाता तो इंडक्शन से उस चार्जेस का डिस्ट्रीब्यूशन अफेक्ट हो जाता। वो भी हम आगे अलग अलग केसेस में देख सकते हैं। आइए हम आगे बढ़ते हैं नेक्स्ट पॉइंट की तरफ। सो पोजी प्लीज बोर्ड को क्लियर करो। थैंक यू पोजी। सो स्टूडेंट नेक्स्ट पॉइंट, मोस्ट कॉमन पॉइंट ऑफ द टॉपिक इलेक्ट्रोस्टैटिक्स, हम बात करेंगे कूलम्स लॉ और सुपरपोजिशन ऑफ फोर्सेस की। सुपरपोजिशन अगर हम बात करें तो सिंपल फिनोमेना सुपरपोजिशन का कई जगह हमने पढ़ा है। फोर्सेस के सुपरपोजिशन में वही चीज़ यहाँ एप्लीकेबल है कि अगर किसी चार्ज पे एक से ज़्यादा फोर्सेस लग रहे हैं तो नेट फोर्स उन सभी फोर्सेस के इंडिपेंडेंट वैल्यूज़ का वेक्टर सम लिया जाएगा। अगर हम कूलम्स लॉ की बात करें तो आई थिंक ऑल ऑफ यू आर वेल अवेयर ऑफ कूलम्स लॉ। 2 पॉइंट चार्जेस के लिए अप्लाई किया जाता है। अगर Q1 Q2 दो चार्जेस हैं, दोनों अगर सेम पोलैरिटी के हैं तो ये एक दूसरे को रिपेल करेंगे विद द फोर्स F। अगर इनके बीच का सेपरेशन R है तो यहाँ पे जो फोर्स की वैल्यू है वो दी जाती है K Q1 Q2 बाई R स्क्वायर। K इज़ द इलेक्ट्रोस्टैटिक कांस्टेंट जिसे लिखा जाता है 1/4 पाई एप्सिलॉन Q1 Q2 बाई R स्क्वायर। एप्सिलॉन इज परमिटिविटी ऑफ स्पेस, जिसमें एप्सिलॉन को एप्सिलॉन नॉट मल्टीप्लाइड बाय एप्सिलॉन आर कहा जाता है, जिसमें एप्सिलॉन आर इज टेकन एज डाइलेक्ट्रिक कांस्टेंट। और एप्सिलॉन नॉट इज द परमिटिविटी ऑफ फ्री स्पेस। फ्री स्पेस की परमिटिविटी ली जाती है यहाँ पे क्योंकि एप्सिलॉन आर होता है डाइलेक्ट्रिक कांस्टेंट, या इसे रिलेटिव परमिटिविटी भी कहा जाता है। रिलेटिव परमिटिविटी इसको इसलिए कहा जाता है क्योंकि एप्सिलॉन आर की वैल्यू होती है एप्सिलॉन बाई एप्सिलॉन नॉट। सो परमिटिविटी ऑफ मीडियम डिवाइडेड बाय परमिटिविटी ऑफ फ्री स्पेस इज दी रिलेटिव परमिटिविटी और डाइलेक्ट्रिक कांस्टेंट। यहाँ पे समझने की चीज़ बहुत ज़रूरी है आपके लिए कि जब कूलम्स लॉ की बात करें तो इसकी लिमिटेशन सबसे ज़्यादा इंपॉर्टेंट हमारे लिए है। लिमिटेशन अगर हम बात करें, कूलम्स लॉ की 2 मेजर लिमिटेशन है। फर्स्ट लिमिटेशन है ओनली फॉर पॉइंट चार्जेस। कूलम्स लॉ सिर्फ पॉइंट चार्जेस के लिए वैलिड है। और लिमिटेशन 2 है बोथ चार्जेस मस्ट बी एट रेस्ट। जब 2 चार्जेस रेस्ट पे होते हैं तभी कूलम्स लॉ उन चार्जेस का नेट फोर्स देता है, और ये चार्जेस ओनली फॉर पॉइंट चार्जेस के लिए ही वैलिड है। अदरवाइज दिस रिलेशन इज नॉट डायरेक्टली एप्लीकेबल। ये चीज़ आपको ध्यान रखनी है। क्यों ऐसा होता है उसका पॉइंट भी क्लियर है कि अगर हमारे पास 2 बड़े चार्जेस हैं जिनके सेंटर ऑफ मास सेपरेशन अगर R लिया जाए, सो इन दिस सिचुएशन एक चार्ज Q1 की वजह से दूसरे चार्ज Q2 के ऊपर इंडक्शन इफेक्ट्स आते हैं। मेटल में इंडक्शन ज़्यादा होता है, नॉन मेटल में इंडक्शन इफेक्ट बहुत कम होता है, ना के बराबर लेते हैं। लेकिन फिर भी आप अगर पढ़ना चाहें पीजी कॉन्सेप्ट वीडियो में ये सारी चीज़ें काफ़ी डिटेल में दी गई। यहाँ पॉइंट चेकलिस्ट के लिए आपको ध्यान रखने हैं कि अगर ये दोनों पॉजिटिव चार्जेस हैं तो एक दूसरे को रिपेल करेंगे, और मेटल है तो ये पॉजिटिव बैक साइड में चले जाएंगे। Dear students, let's start with the topic of electricity. Let's discuss the electric field strength due to a uniformly charged rod. There are two cases. Dear students, let's start with the topic of electrostatics. In electrostatics, we can simply state it as the study of interaction and electrical effects due to static charges, that is charges at rest. Mainly in this particular topic, we are going to deal only with the static charges. That's why it is termed as electrostatics. So very first thing we are going to study about is a charge and its characteristic. There are few facts which we need to understand and discuss. One by one, we just take it up. Like the very first thing is, what do we mean by a charge? We can simply state that charge is a property of a matter due to which electrical and magnetic effects are produced. In your early classes, you might have studied about electricity and magnetism, and all kind of electrical and magnetic effects are produced by a property on a matter which is termed as a charge. We know well that all matter are composed of atoms, so we can simply state all matter in our surrounding which we can see, we can simply say all matter composed of atoms. And if we talk about an atom, we can simply state an atom consists of two parts. One is its nucleus and other is its extranuclear part, in which there are electrons. Electrons are negatively charged, which you all know, and the nucleus consists of some particles which we call nucleons, and majority of the nucleons and nucleus are protons and neutrons. Other nucleons are not in our syllabus, or we can say it is beyond the scope of these lectures. That's why I'm not discussing about other nucleons, that we'll discuss in details of particle physics. And you know well that protons are positively charged and neutrons are neutral. And when we talk about charging of a body, if we just talk about charging of a body, our body can be charged. We can simply state a body can be charged by addition or a removal of electrons from it. Like if we are having a body and if we remove some electrons from the body, and if some electrons are removed, as the body is neutral, we can simply state when electrons are removed, this will be positively charged. As an atom is electrically neutral and the body is made up of neutral atoms, so earlier it was neutral, and if some electrons are removed from the body, it will become positively charged. Similarly, if on a body some electrons are supplied, so these will be excess electrons on the body, due to which we can say it will be negatively charged. So to charge a body, the simplest way out is by addition or removal of electrons. And sometimes students might think, why can't we charge a body by addition or removal of protons? That's quite difficult because protons are there inside the nucleus, and it requires excessive amount of energy to remove a proton from a nucleus. And free protons in nature, it is very difficult to achieve, because these are either in case of hydrogen ion or in case of some bound state that we'll discuss later in nuclear physics. Next point we can talk about charges is, which all of you are aware about, that is like charges repel each other and unlike charges attract each other. There are some more properties. Let's continue on the next sheet. Another fact about charges we can write down as that is charge is a scalar quantity. It does not have any direction, only magnitude we talk about. Another important point about charge is charge is always quantized. In nature, when we talk about transfer of charge, we must keep in mind that it is not continuous, whenever we supply charge from one body to another, it must be in terms of electrons. Like if there is a body and we remove some electrons from the body, it attains a charge Q. Q is the symbol we denote. And the electron is a fundamental elementary particle of which the charge is 1.6 into 10 to the power minus 19 coulomb. So whatever charge the body will attain will be a multiple of this electronic charge. So we can write Q is equals to Ne, where N belongs to a set of integer. Here we can say whatever charge a body can attain will be an integral multiple of the electronic charge. So we can simply state charge is always quantized. Always it can have discrete values. So always remember, on physical object, whenever charge is applied, it must be an integral multiple of electronic charge only. That's why we can say it is not continuous, it is quantized. Another point about charge, we can say that charge is conserved, for which we already discussed that an atom is electrically neutral. So whenever a charge is created by removal of electrons from a body will get positively charged, and an equal amount of negative charge will be there due to removal of electrons. So we can simply state charge is conserved, it can neither be created nor destroyed. So we can say always equal quantity of positive and negative charges can appear or disappear. That means whenever charge neutralizes its equal quantity of opposite charge, then charges will disappear in equal quantity. Whenever these are generated, like the example we have discussed, that will always be in equal quantity only. And another important point about charges, we can say charge is invariant, for which we can say charge does not depend on a reference frame. In whichever reference frame you just have a look on a charge body, its charge always appear to be same. In general, we are talking about. In different cases, we'll talk about other properties related to charge, which may also vary depending on reference frame. But when we talk about charge, it is invariant. Let's discuss about charging of a conductor. Let's discuss a situation. Here you can see there is a metal body on which, say, when externally some electrons are placed onto it. We know well that in case of a metal, charges are free to move. So when these electrons are supplied to it due to mutual repulsion, these electrons will start moving away from each other. And you can see these are distributed on the outer surface of the metal body, because this is the extreme region up to which these electrons can move. That is the outer boundary of the metal. Similarly, in case of another metal, here you can see if some electrons are removed from the body, as the body was electrically neutral, if some electrons are removed from some specific atoms of this metal, positively charged electron deficient zones are created which will repel each other, and these positively charged zones will repel each other and move away from each other, and this positive charge is automatically distributed on the outer surface of body. Or you can also explain this phenomenon in a different way, like when electrons are removed, we can say from the outer surface electrons are attracted towards the inward positively charged zone, due to which these electrons started moving towards the positively charged zone, neutralize the central zone, and positive charges are developed on the outer surface of body. So you can say this is the case when we are adding electron, the body is negatively charged, and this is the situation when the body is positively charged. So here in this situation, we can say it is always a fact for the case of a metal body or a conducting body. We can write down a note which is quite useful for future, that is due to mutual repulsion, always in a conductor, charge reside only on its outer surface, which we already discussed. Whenever some charge is applied to a body, whether positive or negative, it will automatically be distributed on the outer surface of the body. And when we talk about charging, how electrons are added or removed, the phenomena is charging by conduction. Let's discuss it in more detail. Let's continue by conduction about charging, how electrons are added or removed. The phenomena is charging by conduction. Let's discuss it in more detail with the charging by conduction, which is the simplest way to charge a conductor. We can say what we mean by conduction here. We can say on a charged body, charged metal body is connected to another uncharged metal body, charge flows to a neutral body. This is a phenomenon which we call conduction. Here let's discuss it with the help of a physical situation. Here you can see there is a negatively charged body in which there are, we can say, some excess electrons, and there is another metal body which is neutral. And say we connect the two by a conducting wire and we close down the switch. We can say already on the negatively charged body, as electrons are on the outer surface because of their mutual repulsion. Now as the switch is closed and the body is connected with another neutral body, so here you can state in this situation electrons will start moving out from the first body as there is a conducting path available because there is a conducting wire, and the charges started distributing on the other body also. When it will be distributed on both the bodies in such a manner that the mutual repulsion of charges will balance in such a way that no more flow of electrons will take place, then the supply of charge from first body to the another will stop. Here we can say the second body, which was initially neutral, was supplied some excess electrons from the first body through the conduction of this wire. This is called the charging of second body through the phenomena of conduction. This is the way how the body can be charged by using conduction. Similar phenomena may take place and we can easily explain for positively charged bodies also. Students, let's discuss about the charge distribution on an isolated conductor. This is quite an important section which will be used several times in the topic of electrostats. Here we can write down the statement related to this distribution, that is when some charge is supplied to an isolated conductor, it is distributed on the outer surface in such a way that the surface charge density is measured in charge per unit area in units of coulomb per meter square, that we term as surface charge density on a surface when it is charged. So the charge is distributed on the outer surface of the body in such a way that its surface charge density is inversely proportional to the local radius of curvature of the body surface. Like for example, say there is a body which is randomly shaped and it is say a metal body, and if some positive charge is applied to it, here we can say this edge is quite sharp. Here we can say the curvature is very small. The radius of curvature is very small and the curvature is large. So we can say this section of the body surface appears to be a part of a very small sphere. So its radius of curvature is R1, and say in some other region, say here, if we consider another section of body surface, here we can say it appears to be a part of a spherical zone where radius of curvature, say R2, is relatively large, and say in some other zone of body, the radius of, here we can say the curvature is very small. The radius of curvature is very small and the curvature is large. So we can say this section of the body surface appears to be a part of a very small sphere. So its radius of curvature is R1, and say in some other region, say here, if we consider another section of body surface, here we can say it appears to be a part of a spherical zone where radius of curvature, say R2, is relatively large, and say in some other zone, this part can be regarded as a part of a sphere of which the radius is quite large, say this R3, or we can say here R1 is less than R2 is less than R3, or we can say at various region of the surface of this metal, the radius of curvature is different. So the charge when supplied to the body is distributed in such a way that its surface charge density which is denoted by sigma, it is inversely proportional to the radius of curvature of the body. Here the sigma is measured in units of coulomb per meter square, which is the surface charge density. So we can say when charge is supplied, the maximum density of charge on the body surface will be in the zone where radius of curvature is small. Or we can say whenever the edges of this metal is sharp, we can say the charge density is maximum, and where it is relatively large, density is less, and if it is more, density is relatively more less, and almost on the flat surface the density is very small. So we can say whenever charge is applied to the body, it is distributed in such a way that on the sharp edges of the body or where the radius of curvature is very small, the charge density is maximum, or maximum charge is accumulated at the pinpointed edges or wherever the radius of curvature of the metal is small. This phenomena we are going to mathematically derive also later, but we need to use this fact at many places. That's why I'm just giving you the statement of charge distribution on an isolated conductor. So always keep in mind, whenever the conductor is isolated from surrounding, there is no other charge in close vicinity of this body, the distribution is such that its surface charge density is inversely proportional to the radius of curvature. Now let's discuss about charging of insulators. We already discussed about charging of conductor, that is by conduction. Here we know well that insulators are non-conductors of electricity. So as these are non-conductors, we can directly write these cannot be charged by conduction, because conduction of electrons can only take place in metals or which are conductors of electricity. The best way to charge insulators by using friction, and the phenomena we term as friction electricity. Friction electricity you might have studied in your early classes, that is, we can state when two bodies are rubbed against each other due to friction, electrons from one body get transferred to other. Here we can say when two different bodies are rubbed, one body which is more electronegative, which has a tendency to pull electrons more, will pull electrons from the other body which is having less electronegativity. Here we just take an example. Say these are two bodies A and B, and when these are brought close to each other and these are rubbed against each other, we can say as body A is more electronegative, electrons are transferred from body B to body A, due to which after rubbing, when these are separated, body A will become negatively charged and B will become positively charged. This phenomena by which bodies are charged is called friction electricity, because electron transfer has taken place due to friction between the two bodies. You must keep one important note in your mind that using friction, bodies can be charged only if at least one body is an insulator. Because if two metal bodies are rubbed against each other, we can directly state even if electron transfer takes place due to two metals are in contact due to conduction, again the bodies will become neutralized. So two conductors can never be charged by using friction. Frictional electricity works only in case at least one body is an insulator through which retransfer of charge is not possible. Let's discuss an important concept, that is charge induction concept in metals. To understand this concept, let's see a realistic situation. There's a metal body which is initially neutral, but as metal is there, we can say there are plenty of free electrons in the matter which are ready to conduct electricity, but initially it is electrically neutral. Now, if a positively charged body is brought close to this body, we can say this positively charged body will attract the free electrons of this metal. So, free electrons of the metal will start migrating from the surface far away from the charged body to the surface which is closer to the body. Because it is positive, it will attract the electrons. Electrons will start moving from rear surface to the front surface, because of which on the rear surface positive charges will appear and on the front surface negative charges will appear. Now in this situation, if we remove this positively charged body, you can see that the body will again become electrically neutral, and if it is again brought close, we can say that again charge separation will take place due to migration of electrons from rear surface to the front surface. And these charges which are developed due to migration of electrons minus Qi and plus Qi are called induced charges on the surface of this body. So this phenomena here we can say due to external effects, separation of charges in a body is called charge induction. So by external effect, when charges are separated within the body, positive and negative charges are separated within a body, this phenomena we call charge induction. Let's continue with the effect of charge induction on distribution of charges on a metal body. Let's continue on the next sheet. Let's discuss the phenomena of charge induction on distribution of charges on a metal body. Here you can see if we are having a metal sphere which is positively charged, and initially all the positive charges are distributed uniformly on this metal sphere, and say if another positive charge is brought closer, you can see this positive charge will shift some free electrons within this metal sphere from left side to the right side, due to which the charge distribution will be affected. You can see as this charge comes closer, electrons will shift, and on the right side of this body positive charge density is decreased, on the left side positive charge density is increased. Similar phenomena we can understand in case if a negative charge is brought closer, like again say there is a positively charged sphere and a negative charge is brought close to it. You can see this negative charge will repel the electrons of free electrons of this metal sphere, due to which these electrons are shifted from front side to the rear side, due to which on the right side, front side of this charge, you can see that positive charge density is increased, and on the left side positive charge density is decreased. So with these experiments you can very well understand how just bringing another charge close to a charged metal body, the distribution of charge on the metal body is affected. Let us discuss the concept of charge induction in atoms and non-metals. We already discussed that in case of metals, there are free electrons in a metal body, due to which when external charges are brought close, redistribution of charge takes place or induction of charge takes place in a metal body. Let's discuss the cases where there are atoms in which charges are not free to move. Here you can see there is a neutral atom in which we can say there is a nucleus at the center of atom, and there is an electron cloud where we can say there are plenty of electrons revolving around the nucleus. Here you can see that electron cloud is denoted by this green shaded zone. Now say when a positive charge is brought close, like here we have brought a charge, this charge will repel the nucleus because it is positive, and it will exert some attractive force on the electron cloud due to the negatively charged electrons in it. And because of this, the electron cloud gets distorted because it is experiencing an attractive force due to the external charge. And as it is bounded with the nucleus, these electrons cannot leave the atom. The only phenomena which is taking place here is the distortion of electron cloud. And after distortion, you can see the nucleus will be slightly on the right part of the atom, and due to distortion of this electron cloud, the center of negative charge can be taken on the left part of this atom. Or you can say as negative and positive center are separated in an atom, this can be written as a dipole. Or here we can state that due to the placement of an external charge, a neutral atom is transformed into a dipole. This is the phenomena which takes place in case of an atom when charge induction takes place. This phenomena is actually called as polarization of an atom rather than just charge induction. Or we can say in case of an atom, charge induction results in polarization of an atom is transformed into a dipole, where a negative and a positive pole are separated in a very small dimension zone, that is the size of an atom. Similarly, if we talk about insulators or non-metals, the phenomena is similar to this. Here you can see we are having a non-metal body, and in front of non-metal body, say when a charge is brought close, like the situation we can see here, this charge will exert force on all the free electrons of all the atoms in the non-metal body, due to which all atoms will transform into dipoles like this. And these dipoles will align themselves in the direction radially towards this charge, because it will exert electrons of this non-metal atoms directly towards the charge. That's why in this manner the polarization of non-metal takes place. When an external charge is brought close to a non-metal, all atoms will transform into dipoles. Or if a metal is made up of dipoles, all dipoles will align themselves in radial directions towards the external charge. This phenomena we call as polarization of non-metal or insulators. This is the way how we define charge induction effect in case of an atom and in case of a non-metal. Let's discuss about gold leaf electroscope. This is quite an old device which was invented to measure the amount of electric charge. It consists of a vacuum jar, it is like this. Let's see the physical situation of a gold leaf electroscope in which there is a metal rod at the bottom of which there are two gold foils hanging, and at the top we connect a metal sphere. At the bottom of which in which there is the physical situation jar, it is like this. Let's see the physical situation of a gold leaf electroscope in which there is a metal rod at the bottom of which there are two gold foils hanging, and at the top we connect a metal sphere. Now in this situation, when some charge is externally supplied to the metal sphere, say a positive charge is supplied to it, it will be distributed to the gold leaves, and as soon as positive charge is supplied, the leaves will repel each other, and these gold leaves are having a tendency to move away from each other, and their angle of tilt will increase. And we can say if more amount of charge is supplied, the angle of tilt of these gold leaves will be more, and if less amount of charge is supplied, the angle of tilt will be less. So this is the way how the relative measurement of charges were done in quite an old times. So we can execute many experiments on gold leaf electroscope by using the phenomena. And to understand it better, let's discuss a physical situation. Here you can see this is a realistic view of a gold leaf electroscope in which there is a metal rod, there are two gold leaves and a metal sphere on the top of it. And say in this situation, if we bring a positively charged rod close to the metal sphere of this electroscope, we can see due to the positive charge we brought close, the metal sphere will get negatively charged because of induction, and gold leaves will become positively charged, and these will repel away from each other. Now, if this positive rod is brought more closer to the sphere, you can see more electrons will flow from leaves to the sphere. So, leaves will deflect more, and as the rod moves away, the deflection angle of leaves will be less because less induction will take place. Similarly, here you can see if a negatively charged rod is brought close to the sphere will become positively charged because electrons will flow towards the gold leaves. And in this situation, you can see the leaves will deflect away from each other. Similar to the previous situation, as rod is brought more closer, the deflection angle of leaves will be more because more induction will take place. Now say if we just touch the rod with the sphere, just see what will happen in the situation due to conduction. Negative charge will flow from rod to the sphere. First, it will neutralize the charge on the sphere, due to which we can say the leaves will slightly come closer, and later on when it will become again negatively charged, you can see the leaves will again be deflected at a specific angle, and whatever amount of charge is supplied to the metal sphere by conduction, depending on that or some kind of proportional relationship will exist, because of which we can say the deflection is more due to more charge. This is the way how a gold leaf electroscope works. Let's discuss about Coulomb's law, which is one of the important law in electrostats. About this law, we can state that this law gives the interaction force between two static and point charges. This law is mainly used to find out the force between two static and point charges. If there are 2 point charges Q1 and Q2, we know that like charges repel each other and unlike charges attract each other. So if these both are positive charges, these will repel each other with a force magnitude F. And say if the separation between the two charges is R. According to Coulomb's law, according to this law, we can state the magnitude of force is directly proportional to the product of these two charges Q1 and Q2, and the force is also inversely proportional to square of the separation between the two charges. That means it is an inverse square law. And here if we combine the two expressions of proportionality, it gives F is equals to K Q1 Q2 by R square. And in this situation here, K we call proportionality constant. This termed as electrostatic constant, which depends on medium in which the charges are submerged. Value of K we are going to discuss in detail step by step. Here you just keep in mind that the value of K depends on medium, and for free space you can just write down the value. We'll also calculate it and see how it is calculated. The value of K is written as 9 into 10 to the power 9. It is used in SI units, and if you just deduce the units from here, it will be Newton meter square per coulomb square. That is the unit used for the electrostatic constant. About this constant we'll discuss in detail in later part of this chapter. Let's discuss the vector form of Coulomb's law. As we have studied that if there are two charges Q1 and Q2 separated by a distance r, and if say we denote the position vector of charge Q2 with respect to Q1 as the R1 vector, and the force experienced by the charge Q2 is F vector, and that experienced by this Q1 is F dash vector. In this situation, we know that these two are equal and opposite forces as action reaction forces are there. So we can always write that F vector is equals to negative of F dash vector, and in magnitude as these are equal. Here we can write that F vector, which is acting in the direction of this position vector R1. Here we can write it K Q1 Q2 by R1 square multiplied by R1 cap, that is the unit vector in the direction of Q2 from Q1. There is the magnitude of force and there is the unit vector in the direction of F vector. And this can be further written as F vector. We can write, if we substitute the value of unit vector, it is vector upon its modulus. So this will be K Q1 Q2 by R1 cube multiplied by R1 vector. This is the way how we vectorially represent Coulomb's law. And F dash vector can be directly written as negative of F vector. This is negative of K Q1 Q2 by R1 cube multiplied by R1 vector. This is the way how we write the other vector. Or we can say in either direction, if we know the position vector of one charge with respect to other, we can calculate the value of F and F dash. So be careful about these expressions of Coulomb's law in vector form. Dear students, let's discuss the force dependency on a medium. Let's consider a situation when we have two charges Q1 and Q2, and say both of these are of same polarity. They'll repel each other, say with a force F1. In this situation, if I place a neutral body in the surrounding, like if I place a non-metal ball over here, we know one that due to these positive charges, some negative charges are induced over here, or we can say the dipoles of this ball will get polarized, and the positive charges will be repelled away and negative will be developed close to it. Due to which obviously these negative charges will attract these charges toward the ball like this. Or I can say a force FB, this is the force due to the ball will be additionally exerted on both of these charges. It may or may not be equal, say we can write FB1 and FB2. Now in this situation, when the size of this ball will either increase or decrease, certainly the magnitude of FB1 and FB2 will change, but the force F1 which Q1 is exerting on Q2 or Q2 is exerting on Q1 will remain unchanged. Now see, if the size of this ball is increased, certainly net force acting on individually Q1 and Q2 will change because of variation in FB. Now, when the size of ball will increase to such a large extent that both of these charges are submerged into the medium of this material of which the ball was made up of. So we can say in this situation, both of these forces will certainly change. And in this situation, the net force acting on Q1 and Q2 will also change. Now in this situation, we can state when the two charges are submerged in a medium, the force which one charge is exerting on Q2 will not change, but the net force acting on individual charge will change. So we can write down a note over here which is quite important to understand. When charges are submerged in a medium, the force exerted by one charge on another does not change, but due to polarization of medium dipoles, net force on both charges decrease. Why it decrease? Because when the ball will be symmetric with respect to these two charges, the two forces FB1 and FB2 will approach to the same value, that is by symmetry, as well as these are acting in opposite direction. So net force acting on both of these charges will be less than F1, which will be decreased. And we can also mathematically analyze the value, and we'll see how magnitude of force changes due to submerging the two charges in different media. As we already discussed by Coulomb's law, we know that the force between the two charges is given as K Q1 Q2 by R square, where K is the electrostatic constant which depends on a medium. And here electrostatic constant we describe in detail. This electrostatic constant K is given as, the value of K is written as 1 by 4 pi epsilon, where epsilon is called permittivity of medium. This is again a constant parameter which depends on dipole characteristics of the medium, or it decides how much a medium can get polarized when charges are submerged into it. This permittivity is also further written as epsilon is equals to epsilon naught multiplied by epsilon r, where epsilon naught is written as permittivity of free space. This is a universal constant. The value of this epsilon naught is written as 8.85 into 10 to the power minus 12. Units you can deduce from the expression. It is Coulomb square per Newton meter square. In SI units we take. And in CGS units it is also important to consider. It is written as 1 by 4 pi. It is in CGS unit. It is rarely used, but you must keep it in mind, because when you substitute the value of epsilon naught as 4 pi here, for free space, the value of epsilon r is taken as 1. Here you can see the value of epsilon r we write as epsilon over epsilon naught, where epsilon is the permittivity of medium, epsilon naught is the permittivity of free space. So this epsilon r is written as relative permittivity of medium. And obviously for a space, free space, the value of epsilon r is taken as 1. For all other media, as dipole exists, these get polarized and the value of epsilon r is always more than 1. Or we can say the permittivity of medium is always more than 1. We'll also discuss the relation of permittivity with the dipole strength of the medium in later part of this chapter. But you just keep in mind that now for free space, the value of electrostatic constant K can be written as 1 by 4 pi epsilon naught. When you substitute the value of epsilon naught, the result will be 9 into 10 to the power 9. It is in SI units. And if we substitute 1 by 4 pi in CGS units, the value of K is 1. It is in CGS units. Just be careful when you use the value of K in different system of units while calculating force on different charged particles. So if we further analyze the situation, we can write in free space, if we calculate the force between two charges, Q1 and Q2, say both are positive, they'll repel each other with the force F, and the value of F we can simply write it as 1 by 4 pi epsilon naught Q1 Q2 by R square. This is the value of electrostatic constant. And if we submerge the two charges in a medium, here you can write, when we submerged it into a medium, the situation would be like this. The force between the two charges will be, say, F dash. As we already discussed, this force will be less than that in the free space. Now, in this situation, for the medium, if its relative permittivity is epsilon r, in which the charges are submerged, this epsilon r relative permittivity is also termed as dielectric constant. Now, if we are given with a dielectric constant, which is always more than 1, we can write that the value of force F dash is 1 by 4 pi epsilon naught epsilon r multiplied by Q1 Q2 by R square. As epsilon r is more than 1, always the force will be less than the initial force. And this force we can simply write as force which was acting between the two charges in a space divided by epsilon r. Now in this situation, we know the force is reduced because this medium has also exerted a force onto the two charges in opposite directions. Say this force is Fm, due to which this force F dash is less. And if we talk about the force which Q1 is exerting on Q2 and Q2 is exerting on Q1, that will remain same. This will be F and F. So here we can say in medium, we can write for each charge, here you can say F dash is equals to F minus Fm. Because we already discussed that the force which one charge is exerting on another will remain constant, it won't change. Medium exerted another force onto it, because of which the net force, which is F dash, is reduced. So if we substitute the value of F dash, which is F by epsilon r, so we can get the value of force exerted by medium. Force exerted by medium now can be written as F multiplied by 1 minus 1 by epsilon r. This is the force which medium has exerted on the individual charge. There is also a useful expression that will be used in various numerical problems. So just keep it also in your mind. Let us discuss about the limitations of Coulomb's law. As we have discussed that Coulomb's law gives the force of interaction between two static and point charges. These are actually the limitations. So you can directly write that Coulomb's law can be applied only for, number one, as the static charges which are at rest. Because moving charges gives rise to magnetic field also, and when charges are moving, they may experience magnetic force also. And Coulomb's law only account for electric force between the charges. That's why we apply Coulomb's law only for static charges. If charges are moving, Coulomb's law won't give you the net force of interaction between the two charges, as magnetic force also come in picture. Another limitation is it can be applied only for point charges. There are some exceptions for the same, but we can directly state if the charges are distributed on extended bodies. In that case, we cannot consider the center of charge of the body because the charges are distributed onto it. And another fact is in case of a metal body or even in case of a non-metal body, when electric forces are applied, then the body dipoles or the distribution of charge may get changed due to polarizations. And because of polarization, the overall distribution changes, which may affect the net force acting on the body. A simple example we can see, if we are given with a metal sphere which is having a uniformly distributed charge onto it, if it is isolated, everywhere its radius is same, so its charge density will also be same. Now if we place another point charge close by, say it is charge Q1, this charge Q2, then we can simply state if both are positive charges, due to the presence of Q2, it will attract free electrons of the metal body toward right of it, and on right side the charge density will decrease, on left side it will increase. So we can say earlier when it was uniformly distributed, we could have considered the overall charge concentrated at its center, but now it is shifted back. So its center of charge, so-called center of charge, will shift towards slightly left. Now, if we talk about the separation between Q1 and Q2, and if we consider Q1 at the center, then the force between the two can be written as K Q1 Q2 by R square, if small r is the separation between Q1 and Q2. Actually, there is a separation between Q2 and the center of this sphere. But you can see as we have placed a charge plus Q2, overall charge is distributed slightly away from it. Now, due to this, the force between the two will be relatively less because the effective separation is increased. So this won't be true in this situation. Actually, the force will be less than K Q1 Q2 by R square. Similarly, if this charge is negative, then this will repel the free electrons of the metal body, and due to induction, positive charge density closer to it will be more, and effective distribution of charge will be slightly toward right, and effective separation is less. So we can say the force between these two will be less than KQ1 Q2 by R square if Q2 is positive, and this force will be more than KQ1 Q2 by R square if Q2 is negative. Because if it is negative, positive distribution will be right of it and effective separation is less than R, so the force will be more than this value. So always remember, in different cases we apply Coulomb's law only for static and point charges, which are the limitations for applying Coulomb's law. Let's discuss principle of superposition for electric forces. This is quite an important principle to be used in various numerical applications. Let us first write down its statement. It states, one in a system, there are more than two charges, the net electric force on any charge can be given by vector sum of all individual forces acting on it by independent charges of system. This is quite an important rule. Let's discuss it with the help of an application, like say we are having a charge Q0 and in its surrounding there are few charges Q1, Q2 and Q3 placed, and say there are many charges. Now in this situation, say if Q1 is located at a distance R1, Q2 is at a distance R2, Q3 is at a distance R3. And say if we define these distances with respect to Q1, Q2, Q3 in terms of position vectors like distances with at a distance R3. And say if we define these distances with respect to Q1, Q2, Q3 in terms of position vectors like these R1, R2 and R3 are the position vectors of Q0 with respect to the three charges. Now in this situation, say if Q1 is applying a force F1 onto Q0, Q2 is independently exerting a force F2 onto Q0 and Q3 is exerting a force F3 onto this Q0. And these are the independent Coulombian forces applied by the three charges on Q0. And we can write F net on Q0 vectorially can be given by the vector sum of all the forces acting on it, that is F1 plus F2 plus F3. Even we can extend it to any number of charges. So if we substitute the values, then net force acting on Q0 can be given as it is K Q1 Q2 by R1 cube, K Q1 Q0 by R1 cube, R1 vector plus K Q2 Q0 by R2 cube, R2 vector plus and so on. Here I am using the vector form of Coulomb's law we already studied. This is the way we can find out a net force acting on the charge particle due to all the other charges present in the surrounding. For numerical application, it is always easier to resolve all these forces in two mutually perpendicular components, and by using standard unit vectors we can calculate the resulting force. We'll see the same calculation in various numerical examples also. Let's discuss a very important analytical concept related to equilibrium of charged particles, equilibrium of basically three charged particles under electrostatic forces. You can just keep one thing in mind, that if three charged particles are in equilibrium only under electrostatic forces, then it is possible only if our very first statement is the three charges, very first statement is the three charges must be collinear. These must be in a straight line, like say these three charges are placed on the same line, then only these can be in equilibrium. Like for example, there is a charge minus q1, there's plus q2 and there's minus q3. Then it may be possible that onto this charge minus q1, this minus q3 will exert a repelling force and this plus q2 will exert an attractive force, and these may get balanced each other. Similarly, on this q2, the force exerted by q1 and q3 will balance, and similarly on q3, it can also be balanced. Another point which is also a fact is the three charges must not be of same sign. If these are of same sign, it is quite obvious that they'll repel and these can never be in equilibrium. And even for point 1, we can write if the three charges are non-collinear, then they'll form a triangle. And in this situation, say if there's minus q1, there's plus q2, and there's minus q3, then it is quite obvious that this negative charge will repel it, positive will attract it, and these two forces can never be opposite and balanced. So it is obvious that these must be collinear as well as these must not be of same sign. Another important point which is quite useful for these can also be written as the three charges must not be of same magnitude. Because if these are of same magnitude, then again practically it is not possible, because if these charges are of same magnitude, at different separations the forces can never get balanced. And another important fact about this equilibrium is the equilibrium will always be unstable in nature. That is, if it is only under electrostatic forces, if there is an equilibrium only under electrostatic forces, then it will always be unstable in nature. Because if we slightly disturb any of these charges, the force on all these three charges will get disturbed, and because of which the charges will start moving away from the equilibrium position. That's why we can say it is always unstable in nature. For various kind of numerical and conceptual problem, this phenomena is quite useful. So you should always keep this concept in your mind again to handle different kind of problems. Dear students, let's study another important qualitative concept for understanding stable and unstable equilibrium of a charged particle. Here we'll discuss about the equilibrium of a charged particle under the influence of two other external charges. Like say we are having two charges q1 and q1 equal in magnitude and of same sign, and another charge q2 is placed which is exactly midway between the two charges. Now we'll discuss the analysis on q2 if it is of positive sign and of negative sign, about its equilibrium, and say if these charges q1 are fixed and q2 is free to move. And let us consider case 1 when q2 is positive. Now say if q2 is positive, we can say if it is exactly located midway between these two charges, then it is quite obvious that it will be in equilibrium. Now if we slightly displace the charge q2 towards right along the line joining the two charges, then in this situation the separation between q2 and right q1 will decrease. So the force acting on it due to the right charge, which is force towards left, and q1 will exert a force onto it which is toward right. It is Fr. And obviously if this distance is less and q2 is positive, in this situation Fl will be more than Fr, and we can simply state due to this q2 will move toward its equilibrium position again. Similarly, if it is displaced toward left, then again it will have a tendency to come back. So we can simply state Fl is more than Fr if displaced toward right, and in this situation Fr will be more than Fl if it is displaced toward left. So in this situation we can say the charge q2 will be in a stable equilibrium, because wherever we are displacing it either left toward right along the line joining the three charges, it is having a tendency to come back toward equilibrium position. So we can simply state this implies along line joining charges, Q2 is in a stable equilibrium. But let's discuss again the situation when Q2 is displaced perpendicular to the line joining the two charges. If Q2 is displaced away from the line joining the two charges, and if it is positive, we can see this Q1 will repel at Q2, Q1 will repel this Q2, and this Q1 will also repel this Q2, and due to which resulting force on it will be away from the equilibrium position, so it will move away and it won't come back. Similarly, if it is displaced perpendicular to the line joining in other direction, then again it will experience a force due to this Q1 and this Q1 in the direction away from the equilibrium position. So we can say in the direction perpendicular to the line joining the two charges, it will be in unstable equilibrium. Now as Q2 moves away from equilibrium position, if displaced perpendicular to line joining charges, this implies it is an unstable equilibrium if displaced perpendicularly. Now this is the situation we have discussed if Q2 is positive. Let's continue on the next sheet, the situation when Q2 is negative. Now let's continue with the case 2 of the similar situation when Q2 is negative. We just redraw the situation. The two charges plus Q1 are fixed, and exactly midway between them a charge minus Q2 is placed. Obviously, as the separation of this minus Q2 from the two charges is equal, the force acting on minus Q2 due to the two positive Q1 will balance and it is in equilibrium. Let's see what will happen if it is displaced slightly towards the charge toward right along the line joining. As it is negative charge, this positive will exert a force on it, Fr, and this positive Q1 will exert a force on it toward left, that is Fl, and in this situation Fr will be more than Fl because this separation is less. That means as Fr is more than Fl, it will move away from the equilibrium position, and if we displace it toward left, then in this situation the force due to this Q1 is Fl toward left, and Fr toward right will be due to this Q1, and in this situation Fl will be more than Fr. Again in this situation we can say this Q2 will have a tendency to move away from the equilibrium position. So in this situation we can directly write this implies along the line joining charges, Q2 is in unstable equilibrium. And now if we just analyze this Q2, if it is displaced perpendicular to the line joining the two charges, here you can see if it is displaced slightly in upward direction, then this positive charge as being negative Q2, this positive Q1 will attract it, this positive Q1 will also attract it, and net force acting on it will be toward mean position. And if it is displaced downward, again the attractive forces due to Q1 will act, and the resulting force on this negative Q2 will be toward mean position, so it will be having a tendency to move toward equilibrium position. So here we can write along direction perpendicular to line joining charges, Q2 is in a stable equilibrium. This is the situation exactly opposite to the previous case when Q2 was negative, in which along the line joining it was in a stable equilibrium and perpendicular to it, it was an unstable equilibrium. And now as it is negative, along the line joining it is unstable equilibrium, and perpendicular to line joining it is in a stable equilibrium. This concept is again very useful in various kind of problem. So just take a strong review of such kind of small concepts which are quite helpful for you. In this example, we are given that three charges 5 into 10 to the power minus 7 coulomb, minus 2.5 into 10 to the power minus 7 coulomb, and 10 to the power minus 7 coulomb are fixed at the three corners A, B, and C of an equilateral triangle of side 5 centimeter. And here we are required to find the electric force on the charge at C due to the other two. Now, if we just draw the physical situation here, we can see if on the vertices of an equilateral triangle, three charges are placed, this A, this B, and this C. And here we can see that C is a positive charge, A is a positive charge, and B is a negative charge. Now in this situation, due to A, C will experience a repulsive force in the direction away from it, say it is A is a positive charge and B is a negative charge. Now in this situation, due to A, C will experience a repulsive force in the direction away from it, say it is F1, and due to B it will experience an attractive force F2, it is towards the point B. Now in this situation, F1 and F2 we can directly calculate if these charges are Q1, Q2 and Q3. Then we can write F1, which is the force due to A on C, can be given by Coulomb's law as K Q1 Q3 by R square. If we substitute the values, then K is 9 into 10 to the power 9 multiplied by here Q1 is 5 into 10 to the power minus 7 into 10 to the power minus 7 divided by the distance square. Here distance is 5 centimeter, it is 0.05 meter square of this. On calculation, this will result a value, you can easily simplify it, it will be 0.18 Newton. That will be the value of this force which A is exerting on C. Similarly, we can find out the force F2 which is exerted by B on C, that is an attractive force, and its value can be given as K Q2 Q3 by R square, and its magnitude we can again calculate by substituting values. K is 9 into 10 to the power 9 multiplied by Q2 is magnitude, it is 2.5 into 10 to the power minus 7 into 10 to the power minus 7 divided by 0.05 square. On simplifying, we'll get the result 0.09 Newton. As these two forces are acting at an angle 120 degree, we can use the vector summation of these two forces to find the net force. So we can calculate net force on C is this F net we can calculate as by using parallelogram law of vector addition, that is root of F1 square plus F2 square plus 2 F1 F2 cos of 120 degree. If we just solve this expression by substituting the values of F1 and F2, here we'll get 0.18 square plus 0.09 square plus 2 into 0.18 multiplied by 0.09 multiplied by cos 120 can be written as minus half. On simplifying this, we'll get the result as 0.156 Newton. That will be the answer to this problem. In this example, we are given that there are two particles, each of mass 5 gram and charged 10 to the power minus 7 coulomb, placed on a horizontal rough surface at a separation of 10 centimeter. We are required to find the minimum friction coefficient between the particles and the surface so that these particles will remain at rest. In this situation, if we draw the physical case, this is the situation when on a surface there are two particles placed at rest. The separation between the two is 10 centimeter. Each is carrying a charge plus Q. So these two will repel each other with a repulsive force F. Now, if this force will exceed the limiting friction acting between the particle and the surface, the two particles will slide. So here we can say particles will be at rest when the Coulombian force is less than or equal to limiting friction. So here for analysis we can use the limiting value equality. So here Colombian force is kq square by r square, which should be equal to the limiting friction, which is mu mg. So in this situation, the value of coefficient of friction we can get as kq square by mg r square. If we substitute the values, it is 9 into 10 to power 9 multiplied by 10 to power minus 7 whole square divided by m. Mass is 5 gram, that is 5 into 10 to power minus 3 kilogram. G, for simplicity, we can take solution due to gravity at 10, and the separation is 10 centimeters, so it is 0.1 square. If you simplify it, the result you are going to get is 0.18. That will be the answer to this problem. In this example, we are given that two particles A and B having charges Q and 2Q of same sign are placed on a smooth surface over the separation D. And it is saying a particle C is to be clamped on surface in such a way that particles A and B remain at rest under electrical forces only. And we are required to find the charge on C and the location where it should be clamped. Now in the solution, if we draw the situation here on this table, we are given that there are two charges A and B which are placed at a separation D. So if this charge is Q and this 2Q, these two will repel each other with a force, say F1 and F1. And the value of F1 by Coulomb's law, we can directly write it as KQ multiplied by 2Q by D square. Now just to balance these two forces, we must place somewhere in between here, say a charge C, which must be having a charge Q1 and it must be of opposite sign. If A and B are positive charges, this must be negative sign charge, so that it will exert opposite forces on the two charges so that the forces will get balanced. If this force is F2 and this force is F3, then here we can say for equilibrium of A and B, here we can write for A, the forces must be balanced. This will be KQ multiplied by 2Q by D square must be equals to the force applied by Q1 on Q. So if this distance is X, this distance must be D minus X. So here we can write it KQ Q1 by X square. Now in this equation you can see this KQ gets cancelled out and the value of Q1 we are getting is 2QX square by D square. Say this is our equation 1. And for equilibrium of B, here we can balance the forces F1 and Q3 over here. So that will be KQ 2Q by D square must be balanced by K 2Q multiplied by Q1 divided by D minus X whole square. Here K and 2Q gets cancelled out, and on simplifying we are getting the value of Q1 to be equals to Q multiplied by D minus X whole square by D square. This is our equation 2. Now from these two equations, if we equate the values of 1 and 2, here you can see, here just for utilizing the space I am solving it here. From equations 1 and 2, we can equate the values of Q1. So this will be 2QX square by D square will be equals to Q multiplied by D minus X square by D square. So in this situation, on simplifying, I am getting the result to be here. Q gets cancelled out, D square gets cancelled out. On simplifying, I am getting X square plus 2DX minus D square to be equals to 0. Now in this situation, if we solve the quadratic, this is giving us two values of X. One will be root 2 minus 1D, and other result we are getting is negative of root 2 plus 1D. Here we can see that the value of X cannot be negative, as the negative charge is outside the separation between the two charges. The forces can never be balanced. That is, A and B will not be in equilibrium. So this value we can discard, and this would be the position where the charge on C must be clamped so that the two will be in equilibrium. And on substituting the value of X in equation 1, you will get the value of charge Q1 directly. I can write, I am leaving it as an exercise for you to solve it and calculate. from equation 1, you'll get the value of Q1, that will be negative of 6 minus 4 root 2 Q. So these two are the answers of the problem. The charge on C and there's a position from charge on A where it should be clamped for keeping A and B charges to be in equilibrium. In this example, we are given that two identical pith balls are charged by rubbing against each other, due to which a charge of 2 into 10 to power minus 8 coulomb is transferred. That means one ball will be positively charged and the other will be negatively charged, and the charge is given as 2 into 10 to power minus 8 coulomb. And these are suspended from a horizontal ceiling through two strings of length 20 centimeter each. It is also given that the separation between suspension points is 5 centimeter and separation between the balls is 3 centimeter. This is because as the two are oppositely charged, these will attract each other, and finally these will reach another equilibrium position, which is at a separation of 3 centimeter from each other. Now we are required to find the mass of the two balls, mass of each ball. Now in the solution we can see when these are attracted because of this Coulombian force, say this F, and a string will be having a tension T, and both the balls will experience a gravitational force mg in downward direction. So due to this we can say that if balls are in equilibrium, we can balance out these forces on the balls. If the angle from the vertical the string is making is theta, then in this situation we can say the vertical force acting on the bob in upward direction will be F cos theta, and the horizontal force acting on the bob will be F sin theta. Similar free body diagram can be drawn for the other ball also. And in the situation we can write for equilibrium of balls, we can write in this situation if tension is F on it, in this situation we can write the Coulombian force to be F1, and if tension in it is F, so in this situation we can write that F sin theta is equals to the Coulombian force, which is KQ square by R square. In this situation we are given that the separation R is 0.03 meter, that is 3 centimeter, and for equilibrium of forces in vertical direction, F cos theta must be equals to mg. And if these are equation 1 and 2, then in this situation we can divide these two equations 1 by 2. This will result tan theta, which is equals to KQ square by mg R square. If we substitute the value of tan theta here, tan theta can be approximated as sin theta. So in this situation, if this 5 centimeter, this 3 centimeter, this distance will be 1 centimeter, and this is also 1 centimeter. So tan theta can be approximately written as 1 by 20, and it is equals to, if we substitute the value of KQ square, this is 9 into 10 to the power 9 multiplied by 2 into 10 to the power minus 8 whole square divided by m. G we can consider as 10 meter per second square, and the separation is here, this is mgr square. So this will be 0.03 whole square. And on simplifying this expression, the value of mass will get as 8 into 10 to the power minus 3 kilogram, or it can be written as just 8 grams. That will be the answer to this problem. In this example, we are given the two identical point charges plus q are fixed in a gravity-free space at a separation 2L, and another particle with mass m and charge minus q is placed midway between these charges. Now this particle is slightly displaced a distance x perpendicular to the line joining the charges and release. We are required to show that this particle will execute SHM, and also we need to find out its oscillation period. In this situation, say if these are the two charges plus q which are fixed, at center if we place a charge minus q, we already studied in previous articles that the particle will be in a stable equilibrium. As being a negative charge particle, it is in a stable equilibrium for its displacement perpendicular to the line joining the charges. Now if this particle is displaced by a distance x, then this minus q will be pulled toward these two charges with a force F, and say if this angle is theta, it will be experiencing a restoring force. This restoring force we can write as 2F cos theta, and in this triangle, as this length is L, cos theta can also be substituted. Here twice of F is given by Coulomb's law, that is KQQ by x square plus L square, and cos theta we can write as x by root of x square plus L square. So student, now we'll start with a study of electric field. We'll discuss some facts about electric field which will explain the phenomena, how electric field exists, and how we need to visualize the phenomena. The very first point about electric field we can keep in mind, it is similar to gravitational field, where in the surrounding of a mass everywhere gravitational field exists. Here we can write a region in surrounding of a charge where any other charge in surrounding of a charge, a region in surrounding of a charge